So now they want the probability of getting a 5 given that the circle is orange. So the given that, you want to narrow in your focus to just the orange balls. So there are 3 orange balls, and that's like your new total. That's going to be your new denominator, and only one of those balls is a 5. So just 1 out of the given 3. So 1 out of 3. That given that is always the denominator. Zoom in your focus to the given that, that'll be your new denominator. So 1 out of 3 for that. For number 9, they want a red number given that the circle is orange. So again, we zoom in our focus to those 3 orange balls. So there's only 3 that we're looking at, and 2 of those orange balls are red. So 2 out of 3 for that. And that's it. Moving on to 13, they want a red figure given that an even is selected. So we have 1, 2, 3 even numbers, the 2, the 4, and the 6. So we're zooming in our focus just to those 3 numbers, the 2, the 4, and the 6. That's our given. And of those numbers, we want to know how many are red. So looks like just that red 4. So there's just one of those 3 numbers that are red, so probability is 1 out of 3. And so now on 17. So 17, we want the probability of getting a 4 given that the color is purple. So this wheel is divided into 12 pieces. We're given that it's purple. So there are 1, 2, 3, 4, 5 purple pieces that we're looking at. So there are 5 purple pieces that we're looking at, and of those, just looking at the purple pieces, just one of them is a 4. So 1 out of 5 is our probability. What we want over how many we know we're given. 21, a number greater than 4, given that the color is purple. So again, there are only 5 purples that we're given, and we're going to zoom in our focus just to those 5. And of those 5 purple pieces, we want a number greater than 4. So not including the 4, just greater than it. So the 9, the 11, and the 12 are the ones that we want. So 1, 2, 3, right? The 9, 11, or the 12, there's 3 that we want out of 5 that we know we're given. So 3 out of 5. On to 25. So for 25, let's see, assume that a hat contains 4 bills, a $1 bill, 5, 10, and a 20. 2 bills are to be selected at random with replacement. Construct a sample space and find the probability that both are $1 bills. So we could pull so to construct our sample space, we could pull a 1 and a 1, 1 and a 5, or a 1 and a 10, or a 1 and a 20. Or we could start with the 5s. We could pull a 5 and a 1, a 5 and a 5, a 5 and a 10, or a 5 and a 20. Or we could start with a 10. We could pull a 10 and a 1, a 10 and a 5, a 10 and a 10, or a 10 and a 20. Or we could start with 20. We could pull a 20 and a 1, a 20 and a 5, a 20 and a 10, or a 20 and a 20. So this is my sample space. I've listed out all of the possibilities, all of the possible ways to draw 2 bills. and they want the probability that both are $1 bills. So the only one of these that has both $1 bills is that one right there. So there's one possibility that we want out of the 1, 2, 3, 4 times 1, 2, 3, 4, 16 possible total. So just 1 out of 16 for number 25. Looking good. So moving on to 29. So for 29, 2 dice are rolled, one after another, construct a sample space, and determine that the probability of the sum of the dots is a 6. Alright, so when I construct my sample space for this one, and I could have done this on the last one, but I'm going to say dice 1, I could spin a 1, 2, 3, 4, 5, or 6. And on die 2, I guess I should say, oh well, I could spin a 1, 2, 3, 4, 5, or 6. So now, instead of making a sample space and saying 1 and a 1, a 1 and a 2, a 1 and a 3, 1 and a 4, and listing all of them out, I'm just going to go straight for the sums because that's what they're asking me to do here. They're curious about the sum. So if I rolled a 1 and a 1, my sum would be a 2. If I spun a 1 and a 2, my sum would be 3. 1 and 3, 4. 1 and 4, 5, 6, 7. There's lots of patterns in this chart. If I spun a 2 and a 1, my sum would be 3. A 2 and a 2, 4, 5, 6, 7, 8. And we just keep filling in the chart. 5, 6, 7, 8, 9, 10. 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. So there's my sample space. Now I can use that sample space to find the probability that the sum is 6. So looking at those, there are 1, 2, 3, 4, 5 ways to roll a 6. So 5 that we want out of 36 possible total. So just 5 out of 36. And then for number 33, they want a number greater than 7 if the second die is a 5. Alright. So let's get rid of these. So they want a number greater than 7 So they want a number greater than 7 if the second die was if the second die is a 5. So that if the second die is a 5 is our given that. We're given that the second die is a 5. So we're focusing on second die is a 5. We're focusing on just those sums. So the only possible sums we're worried about are 1, 2, 3, 4, 5, 6. Only 6 possible choices if we know our second die was a 5. And zooming in on that, of those possible choices, they want to know that it was greater than 7, that a number, that the sum total a number greater than 7. So we'll take the 8, the 9, 10, or 11. So 1, 2, 3, 4 possibilities that we want out of the 6 that we know we're given. So 4 to 6 simplifies to 2/3. That's number 33. So, perfect, looking good. And on to 37. So for 37, one hurricane is selected at random. Determine the probability that it had damages of at least 20 billion, given that it was a category 4. So you look, and you're given that is that it's a category 4. So we're zooming in our focus to just, looks like Katrina, Charlie, and Hugo. So Katrina was 80, and Charlie was 15, and Hugo was, oopsie, wait, that it had damages of at least, I'm sorry, we don't care about how much damage it did. There are just 3 hurricanes that we're looking at, just Katrina, Charlie, and Hugo. And of those 3, how many of them had damages of at least 20 billion? So Katrina definitely did. It had 80, so we'll count him. That's 1. Charlie, 15, not enough. And then Hugo, 7, not enough. So just 1 out of the 3 had damages of 20 billion. So we've narrowed in our focus to category 4. There was 3 of those, and only 1 of those had damage greater of at least 20 billion. So that's 37. Now 41. So for 41, let's see. If one of these vehicles is selected at random, determine the probability that the vehicle was a car. So there are 2,461 total that we could pick from. And the ones that were cars, if you look in the sum of the car column, 1,462 of them were cars. So there are 1,462 cars out of 2,461 total. You just take those and divide that. So 1,462 divided by 2,461, and you get 0.594, and I'll round to 1. So got that. And then 45, the vehicle was a car given that the vehicle was an easy pass. So now, now we're just looking at the cars that use the easy pass. So, under easy pass, if we know we use the easy pass, we're restricted to those cars that use the easy pass. There are only 843 cars total that used easy pass. So 843 that used the easy pass, and of those, 527 were cars. So that's that. Let's punch that in. 527 divided by 843, and we get 0.6251. And that's that. So now